This is lesson 3 from chapter 16 for honors chemistry. We're going to be talking about colligative properties. And if you look at the word colligative there, it comes from the Greek, which means relating to the number. Relating to the number. And here we're talking about properties of solutions that depend upon the number of particles that are dissolved. And that number of particles, the word number, we would usually often use moles, and the particles can be atoms or molecules or ions, which are the usual particles that we work with in chemistry. Now, something else about this opening slide is that here we have these wood frogs that have natural antifreeze. In other words, they are able to survive in environments where the water is frozen. In fact, they can survive being frozen. How is that possible? Well, they don't get frozen solid because in their fluids of their body, they have a compound that is dissolved that acts as a natural antifreeze. In other words, it depresses the freezing point, so even though the pure water would freeze, solutions that have these antifreeze particles in it would not be able to freeze yet. Now, another interesting aspect of this slide is it illustrates a huge brand new field of science called biomimetics. Or you can also find it under biomimicry. Now, you know what it means to mimic somebody or something. Biomimicry is the branch of science where we look at plants and animals and the compounds that make them up, and we look to see if maybe there's a molecule, maybe there's a nanomachine, maybe there's a design, maybe there's a relationship that we can take advantage of, that we can utilize and put to solve a particular problem. Another example, besides looking at ways in which to have biological, naturally occurring antifreeze molecules and how to use them in living things, would be, think of the woodpecker. The woodpecker bangs its head many, many, many times, day after day, against a tree, trying to get grubs and worms and little bugs out of the bark. How is it able to do that without having a concussion, without going crazy, without killing itself? And so in the head and in the entire woodpecker's body, you have muscles and ligaments and bones and beat structures and a nervous system and a brain system, all of which is designed to take this incredible trauma and not be harmed. And so you can look at the woodpecker, which has been done, and figure out better ways to design those black boxes that an airplane might carry that you hope survives a crash. This is all examples of biomimetics or biomimicry. The flagella of bacteria actually is connected to a rotary motor made up of about 35 proteins that can spin upwards of 1,000 times a second and stop in a quarter turn in reverse. And we only discovered these things in the last several decades, long after somebody actually invented a rotary motor. So this is another example of biomimicry, where we are trying to copy some of the designs and the ingenuity that God has already created into every single bit and aspect of his creation. So colligative properties depend upon the number of solute particles. We don't care so much in terms of what they are, what their identity is. We don't care if they're atoms or molecules or ions. Now later on, we're going to modify that statement just a little bit when we get to the Hoff factor. But that's towards the end of chapter 16. Mostly the more particles, regardless of what they are, the more a certain property of the solution is going to be affected. Right now, we're going to look at 3 in particular. Later on, we're going to look at osmotic pressure. So these 3 are freezing point depression. In other words, when we add particles to water or some other solvent, it's going to cause the freezing point to be lower. In the case of water, instead of freezing at 0 degrees, now maybe it's going to freeze at -5 or -7 degrees because of the addition of those solute particles. And the more particles, the more you lower the freezing point. Boiling points get elevated. The more particles you add, let's say, for example, to water, the higher you have to heat the water before it's going to begin to boil. And then finally, vapor pressure. Vapor pressure, if we're talking about a container, like a beaker right here, and that's got a solution in it, and we have a cover on top of the container, some of the particles of this solution are going to evaporate, and at a given temperature, you're going to have an equilibrium where some of the molecules in the liquid state or particles will go into vapor, and some of them that are in the vapor will go back down into the liquid, and you reach an equilibrium. When you reach an equilibrium, you can then measure the vapor pressure of the vapor that's in this closed container. Well, the point is that if you add some solute particles, and I'm going to make them orange, if I add some solute particles and dissolve them here in the liquid, that's going to reduce the number of solvent particles that can evaporate because some of the solute particles are in the way. And now my vapor pressure is going to be lower because not as many of the particles can escape into the vapor state. So when we talk about these particular things like freezing point, boiling point, vapor pressure, these different properties, we often use molality. And the difference between molality and molarity is the denominator that has the same numerator, moles of solute. But in the denominator of molarity, we had the volume, usually in liters, of the solution. We didn't care or need to know the actual volume of the solvent, just the overall solution, which is why we could use a volumetric flask. Here we want, instead of volume in liters, we want kilograms. And instead of solution, we want of the solvent. And why are we suddenly using kilograms when we've been using grams all year? Because typically we're talking about a liter or 2 liters or large volumes of solvent, in which case it's easier to measure their mass than it is to find a container that can hold their volume. And with measuring their mass, you can get that to the 10th to the 100th place on a scale a whole lot easier than you can get to the 10th or the 100th place of a milliliter. So one more time then, this is yet another equation that's simply A equals B over C. And you have to find one of these, and you're given the other two. And typically, your moles often have to be converted to grams, or you begin with grams and you have to convert it to moles before you can plug it into the equation. So here's an example of calculating the information you need from that particular formula. Let's say that for a particular lab, you need a half molal solution, and notice that molal is lowercase m. You need a half molal solution of table salt, sodium chloride. So how are you going to make that? Well, if you need a half molar solution, you can use, and you want to put it into a liter of water. 1 liter of water is 1,000 milliliters of water, and the density of water is 1.0 to 2 significant digits. So that makes this 1,000 grams, which makes it 1 kilogram. So to get your extra significant digits, rather than using a volumetric flask or a beaker or something, we mass it. We get 4 significant digits there. 1 kilogram of water, we put it into our container, and then we need to put in a half a mole of solute. Well, in order to know what half a mole is, you've got to convert you have to use the molar mass of sodium chloride. So if you know the molar mass of sodium chloride, which is about 58 grams per mole, and you multiply by half a mole, you get 29.3 grams is how much you have to mass out onto your piece of paper and then dump it into the flask and then thoroughly dissolve it. And then you will have a 0.500 mole of solution. Why 3 significant digits? Well, this number here had 3, this number there had 3, though if I was using the periodic table, I would have gone to 4 significant digits here. This goal had 3 significant digits, and that's why my answer has 3. Freezing point depression. When you put solute into solvent, it's going to depress the freezing point, make it harder to freeze, interfere with the crystallization process. So you're going to have to get to a colder temperature, because even though you might be below freezing with your salt water, those salt waters are interfering with the ability of the water molecules to create that crystal lattice structure in those hexagon shapes. And notice we have the negative sign here, because if we want to know the new freezing point, we have to take the old freezing point, or the original one, or the one when the solvent is pure, and we need to subtract this change in freezing point that results because we've added some solute to the solvent that's interfering with the freezing process. And of course, this time of year with winter, you see this a lot. Why do we put salt or different kinds of salt or mixtures of salt and beet sugar onto roads and sidewalks and driveways? It's because whereas at a temperature below freezing, rainwater or precipitation would freeze and form ice on the surface, the presence of this salt in the back of the truck that's being distributed here depresses that freezing point. So now the temperature has got to get -5, -10 degrees before the roads freeze. And of course, typically, especially with a little bit of heat from friction of tires, and sometimes the black or asphalt or the concrete absorbs some of the solar heat, usually temperatures often hover around 30 degrees or so, so adding a little bit of salt does depress the freezing point enough. Now you can add beet sugar, which is going to be a molecule. You can add sodium chloride, which is actually going to give you double your money's worth, because it's going to spread out into 2 particles instead of just 1, and that means it's going to multiply your change in your freezing point by a factor of 2, theoretically. Or we might even use something expensive like calcium chloride or calcium chloride, because that's going to give me 3 particles that can interfere with freezing. Triple the depression of the freezing point, theoretically. And we'll talk more about that again at the end when we talk about Van 't Hoff factor. The ocean, of course, has salt dissolved in it. The average salinity of salt in ocean is about 3.5%. And it varies substantially, of course. If you're near melting icebergs, it's going to be less than that. If you're near the mouth of a river dumping fresh water in, it'll be less than this. If you're in warm ocean water in the middle of the Indian Ocean, it can be more than that, because the higher the temperature, the more salt you can dissolve in it, as you learned in a previous screencast earlier in the chapter. And so ocean water does not freeze at 0 degrees Celsius or 32 Fahrenheit, but it freezes at a temperature lower than that because of the presence of salt in there. All right. Dissolving salt elevates the boiling point, depresses the freezing point, and we can calculate how much. It elevates the boiling point. We'll get to the calculations in a minute. So when you put antifreeze into the coolant water in the radiator system of your car, that antifreeze is also an anti-boil. Not only does it keep the water from freezing when the temperature gets to be 0 degrees by depressing the freezing point, it also interferes with the boiling point. And car engines can be very, very hot. And you don't want the water in your car engine to boil over like it's doing here. And so the antifreeze raises the temperature at which the water will begin to boil. So, how much? What are we talking about? And so you can see here that how much your boiling point is going to be elevated depends upon the molality. So the change in temperature of my boiling point is proportional to the molality. Notice we use the lowercase m, not the uppercase M italicized like we did with molarity. So it's proportional. And as you might guess, well, if we want an equal sign, we are going to need a proportionality constant. And so you can have a boiling point constant, and you can also have, for your freezing point depression, you can have a freezing point constant. So where do we find these proportionality constants? Well, some of your math problems might ask you to calculate the constant, and of course, in order to do that math problem, you would have to be able to calculate the molality, and you'd have to be given the change in boiling point or the change in freezing point. Which, by the way, when you do your homework, be very careful. Does the problem give you the change in temperature? Does it give you the change in temperature? Or does it give you the initial temperature? Or does it give you the final temperature? If it gives you the initial and the final temperature, of course, you can calculate the change in temperature. Make sure you know which is which in the problem. So you can calculate your change in temperature if it's not given to you, and you can solve for your constant. But most of the time, your constant, you're going to look it up in a chart. So here's the actual equation, and again, Notability messed up the PowerPoint arrangement, but that's okay. And you're going to look up the boiling point constant and the freezing point constant in a chart. And sometimes they put the negative sign here for freezing point, sometimes they don't. You're supposed to know that the freezing point lowers it and boiling points elevate it. And you have a similar formula then for your boiling point. And boiling points, of course, always go up. And so here are some of those values in some charts. And you'll notice something that jumps right out at you. And that is that water, which is the most common of all solvents, sometimes called the universal solvent, though of course it doesn't dissolve everything in the universe, which is a good thing because you hate it when the beaches dissolve, and you hate it if you jump in the water and you dissolve. So it's not technically, literalistically, a universal solvent. Be that as it may, you'll notice how low your constant is compared to so many other solvents. This means that you can add an awful lot of solute to water, and it only depresses the freezing point a little bit, and it only elevates the boiling point just a little bit. And that's a really good thing for all the things that live in the ocean and live in the creeks and the rivers and the seas, that the freezing points and the boiling points, as salts and sediments are in the water, that those temperatures don't get really high and really low when we have extremes in temperature. Otherwise, all the animals might not be able to survive that. So as usual, and as you should expect as a scientist, God's figured this out pretty well. We should not be surprised when we see values like this in terms of the very incredible balance and equilibrium and design of the systems that make up our planet. If we were to graph the freezing points and boiling points, we have temperature along the x-axis. we have vapor pressure. Now we're talking about vapor pressures, but we could have a similar kind of graph if we were talking about freezing points and boiling points as well. And you'll notice that in red, you have pure water. And so in pure water, just for the record, there's this interesting point where at this point, which is called the triple point, if you had this temperature slightly above zero, like point something or other, and if you had this pressure, which is very, very low, very, very low pressure, the scale, by the way, would be a logarithmic scale. This triple point, you can have water exist in all three states at the same time. You could have a closed container where you would have liquid water and ice and water vapor all at the same time in the same place. The line itself shows equilibrium. This is the equilibrium at different temperatures and pressures between ice and water vapor. In other words, you go back and forth in equilibrium between solid and gas. We call that sublimation and deposition. Now this line right here, you're in equilibrium between liquid and vapor. And you have liquid evaporating and vapor condensing at the same time at these different temperature pressure combinations. And this is another equilibrium line between solid and liquid, solid and liquid. And if you're at this temperature pressure, anywhere along that line, your liquid is freezing, but also some of the solid is melting. Now, if you add a solute, you're going to notice that your boiling point is going to go up, and your freezing point is going to go down. Remember, temperature is along the x-axis. So your freezing point gets depressed, your boiling point gets elevated. Now, it is not true that the width of this space and the width of this space is identical. If we go back to our chart, you'll notice that this number here is more than 3 times bigger than that number. But the point is, it is a measurable difference. Now, glucose, which is not an ionic compound, so this would be a molecule. It's a simple sugar, c16H12O6, glucose. Learned a lot more about that in biology. If you were to put 3 moles of glucose into some water, you would be putting in 3 moles of particles. And we call that a Van Hoff factor of 1. 3 moles of particles from 3 moles of sugar, because sugar does not break apart into parts like salts do. That's a Van Hoff factor of 1. Now, you'll notice the approximate sign, because not all of these sugar molecules are going to get yanked apart. So when we put 3 moles of particles in water, we might only have 2.95 actual particles that are dissolved by 2.95. That means some of my particles might be double or triple glucose molecules stuck together. Now, if I put sodium chloride into water, I'm going to get 2 particles. Polar water is going to yank my sodium chloride into sodium ions and chloride ions, and so I'm going to get double my money's worth, so to speak. For every 3 moles of sodium chloride I put in, I'm going to get 6 moles of particles, twice as many. Actually, approximately twice as many, because not every sodium chloride is going to be yanked apart. If I have a really dilute solution, then I can expect there to be enough water molecules to get pretty much a complete splitting apart of every sodium chloride in the crystal. And my Van Hoff factor will be very, very close to 2. But if I have a more concentrated salt water solution, certainly 1 molar even 0.5 molar, I'm not going to be very close to 2 because I'm going to have a lot of sodium chlorides that won't separate. And so my Van Hoff factor might be like 1.7 or 1.82 or something like that. If I put in 3 moles of calcium chloride, that's going to break up into 3 ions, and I'm going to have 3 times the number of particles interfering with freezing, interfering with boiling, interfering with evaporation. And therefore my Van Hoff factor will be closer to 3, but not quite exactly 3, because some of the calcium chlorides will not entirely separate, especially as the solution becomes more and more concentrated. And so we represent the Van Hoff factor with the letter I. Sometimes you see it at the end of the equation, sometimes you'll see it at the beginning of the equation, and when you have a molecule that is non-ionic, like glucose, you ignore the Van Hoff factor because it's basically 1. You would have to worry about it if you began to get a relatively concentrated solution. But for salts, you always need to be thinking about the letter I. So when you do your homework, take your test. If you're doing a colligative property problem of elevated boiling point, depressed freezing point, depressed vapor pressure, increased osmotic pressure, if the solute is a ionic compound, salt, make sure you consider the Van Hoff factor. And unless you're given a chart that gives it to you specifically, you'd have to round off to the nearest whole number of 1, of 2, or 3, for example. You have the same thing with the boiling point elevation, the Van Hoff factor. And you're always going to get your constant from a chart. You would not have to memorize it. This also depresses the vapor pressure. The vapor pressure, and again, I'm going to draw a nice big beaker here. You can see the beaker because you've got your little lips in the side, and we've got liquid inside. You can see it's got waves, of course. And so there's my solvent, okay, inside the liquid, and I'm going to put a cover, and let's redraw the beaker, and I'm going to put a cover over the top so I have a closed system that can reach equilibrium. And now I'm going to draw a couple of my solvent particles that have evaporated, creating pressure. There is a vapor pressure, or PVAP, that can be measured above the water, vapor pressure, or whatever the solvent happens to be. Now, as soon as I add solute, pictured here in red, some of those solute particles will be across the surface, and now not as many solvent particles can escape. So I'm going to go to my eraser, and I'm going to erase some of my solvent particles, and now my pressure has gone down. My vapor pressure has been lowered because of the addition of the solute. And that's what they're going to show you here. I think my drawing is maybe not as nice, but explain what was going on very well. And here my greenish liquid means I've added a solute, and that solute interferes with the ability to evaporate, which lowers the vapor pressure. And so once again, my vapor pressure is proportional. My change in the vapor pressure is proportional to the molality. The negative sign, of course, reminds me that it is depressed, and I would need a constant, a vapor pressure constant, in order to turn this proportionality into an equation with an equal sign. Sometimes we multiply the pressure. Instead of using that equation that I just showed you, we multiply it by the mole fraction. When we multiply it by the mole fraction, we're finding what fraction of the vapor pressure is due to the solvent, and what fraction of the vapor pressure is due to the solute. So if my solvent is represented by letter B, and my solute is represented by the letter A, if I multiply that by the fraction, then I can get the new vapor pressure. So my change in vapor pressure is going to equal my mole fraction times my initial pressure when the solvent is pure. So remember what a mole fraction is. I have to convert my grams of solute into moles, and I have to convert my grams of solvent into moles, and I add up the sum of my solute, sometimes there's more than one solute, and solvent, that goes in the denominator, and the moles of what I'm interested in goes in the numerator. So I add up the moles of everything in the solution, that's the denominator, and the moles of what I want to find the fraction of goes in the numerator. You could do the same thing. We could find the male fraction and the female fraction of students in the chemistry classroom. We could put the moles of guys up here, or just the number of guys, and guys plus girls down here in the denominator to get the guy fraction, and we can find the girl fraction. We multiply by 100% if you want to find percentage. And here's an example of finding the mole fraction of ethylene glycol, which is the commercial name for antifreeze. And we can find the mole fraction of ethylene glycol and the mole fraction of water that's present in the solution that's in the radiator of my car. Next time, we will begin to talk about osmosis. It's not closing.